Equating Newton's law of gravitation with our old weight formula can lead us to a formula for calculating the acceleration or the strength of gravity which any mass possesses. So these, I'll rewrite it since it's on the previous page. We can put these two things together. Fg could cancel out, mass of the small object could cancel out. Acceleration of gravity equals the gravitational constant times big M times the square of the distance. So here's how this can work. Calculate the value of G at Jupiter's surface. So we are calculating G for Jupiter based on this formula. We need to know a few things. First off, the mass of Jupiter. And so we look at our sheet and it says 317.892 times the mass of the Earth, 6 times 10 to the 24th kilograms. So Jupiter is about 318 times more massive than the Earth. The radius of Jupiter. So if you look at the sheet, it has the equatorial diameter. So that the diameter at its largest, 142,984 kilometers. That's diameter, and we need radius. So we're going to divide that by 2. 71,492 kilometers. For this gravitational formula, we need to change this to meters. So 1 kilometer, 1,000 meters. So we have 7.149 times 10 to the 7th meters. So let's use this formula that we just found. Acceleration of gravity is big G times the mass of the object times the radius squared, and plug in our numbers. So before we go too much further, let's go ahead and cancel out some units just to clear things up. So on the bottom we have meters, which is going to be squared. As usual, this squared also applies to the number, so don't get rid of your 2. Don't get rid of that exponent. So the meters on the bottom cancels with meters squared on the top. Here this is a little bit different. For kilograms, we have kilograms over kilograms squared. So we can cancel one of these, and that gets rid of the squared, but we still have a kilograms left. So AG equals, so here's 24.9. And let's pause and look at the units just a little bit more in depth. So write this down. Here's what we had. Newton meter squared per kilogram squared. Times kilograms times 1 over meter squared. So the meter squared cancels, square here and the kilograms cancels. So we have newtons per kilogram. And we have to know what this means. Newtons per kilogram is not really a good unit, especially when we're talking about acceleration. So what is a newton? It's a kilogram times a meter divided by a second squared. Kilograms will cancel out, and that leaves us with meters per second squared. 24.9 meters per second squared, and that's approximately 25. In the few instances where we calculate things based on Jupiter, we typically use 25. Just like with Earth, we typically use 10. Number 7, calculate the value of G 250 miles above the Earth's surface. So method 1, we're looking for G, and that is big G times the mass of the object divided by the radius squared. In this case, the object is the Earth. Here's big G, here's big M, the mass of the Earth. And the radius of the Earth, we generally use the number 4,000 miles. So if we are 250 miles above, so here's the Earth, and now we are 250 miles above, and this picture is not to scale. 4,250 miles. Again, change it to meters. And we need to square this entire quantity. So canceling out some units, we have meters squared on the bottom, meters squared on top. Kilograms, we'll cancel with this one. And again, we have newtons per kilogram for our units. So G equals 8.56 newtons divided by kilograms, meters per second squared. Method 2, a little bit different. So here is the original value for G that we have, 9.8 meters per second squared. And then we have this ratio of the radii. So the original radii, 4,000, and the new radii, 4,250. And we have to square this quantity. Remember, because 1 over r squared. And you'll get the same number here, 8 point, or at least close, 8.68 meters per second squared. So if you understand what's going on with this method. It's an acceptable one to use, but and my recommendation is use method 1. So it's just too easy for students to confuse this method, and they get the radii flipped upside down and strange things happen. So here's some applications of gravity. Ocean tides occur because the moon's gravitational attraction acting on the ocean waters of the earth. But doesn't the moon pull on the earth and the water as well? Explain why tides occur and why there are 2 high tides and 2 low tides every 24 hours, or approximately. So let's draw a picture for this. So this is the Earth. Here is the radius of the Earth. And here's the moon. So this is what happens. The moon is pulling on the earth and the water. And so you get a slight bulging of the water. So here's what a high tide would look like. Something like this. And that's overly dramatic. But for the sake of the picture, the water bulges out like this. And the same thing on the other side. It does it to the other side as well. And so let's label these. This is a high tide here and here. And this is a low tide. And this is a low tide. So what's happening is the moon is pulling on the water, and it's also pulling on the earth, and everything is being stretched in this direction. So if you look from this point where the water is to the center of the moon, and this is not to scale, so like that, this is a distance of 59 Earth radii away. From here to the center of the moon is 60 Earth radii. So using r as the Earth's radius, the Earth is 60 times the radius, 60r from the moon. The water on the moon side is 59 times the radius, or 59r from the moon. If the distance is less, the attraction is greater, according to the formula. So the water is in effect pulled away from the Earth. The water on the opposite side from the moon is 61 radii from the moon. Since the Earth is closer to the moon than this water, the Earth is in effect pulled away from this water. Thus, there are high tides on 2 parts of the Earth at the same time. Since the bulges of water have to come from somewhere, there are low tides at other positions. Which exerts a greater force on the Earth, the sun or the moon? The sun. Then why doesn't the sun cause ocean tides instead of the moon. So first, let's look at the Earth-Moon attraction side of things. So let's look at the near side. And this is really that method 2 for gravity from the previous page. But here's how it's going to work. So the near side, so there's a fraction and it's going to be squared. So remember the radius squared. 1 over the radius squared. It was that inverse square relationship. So if we're just talking about the distance between Earth and the Moon, it would be 1 over the radius squared, 1 over 60r squared. But we're looking at the ratio here, and so in order to get the ratio, we're going to put this 59r on top. And so we see that this is the percentage of, not the difference of the, basically the difference would be this 3.31%, closer to the moon. From the far side, so the bigger number goes on the bottom, 61r, and the smaller one on top. And we're talking about 96.75%. So these are the numbers of how the gravity relates as far as the moon with the closer side versus the far side. But to make things maybe make a little bit more sense, let's compare the Earth-Sun relationship. Because here we see that the near side could experience 3% more and the far side 3%. There's a big variation here. So first let's look at the relationship here. 93 million miles from the Earth to the Sun. Over 4,000 miles, which is the radius of the Earth. And so if you divide this, it tells you in terms of how many Earth radii away is the Sun. 23,250 times the Earth radius is the Earth to Sun distance. So let's look at it in terms of the near side. So for the near side, we've got 23,250 times r, and this closer side is 23,249 times the radius. So there's the near side, look at the far side. The far side is 23,251 times the radius. And this is also 99.99%. And so the effect of the Sun's gravity, well, yes, it is much stronger, the variation is much smaller. See, this is the variation of the moon's gravity working on the tides. This is the variation in the Sun's gravity affecting the tides. And so it's 0.01%, or maybe even lower than that the Sun affects the tides. Newton's law of universal gravitation is one of the greatest scientific achievements ever. We use this law to study the universe, and we use it to keep satellites in orbit around the Earth. There was so much faith in the law that when Neptune began acting strangely and was seemingly disobeying gravity, astronomers did not question Newton's law, but instead they predicted the existence of another planet. And they began to search for it. The search resulted in the discovery of Pluto in 1930. There's a stained glass window in a cathedral in Cambridge, England, depicting Isaac Newton perched on the shoulders of several other people. Had he just scored the winning touchdown? No. With the window is this quotation from Sir Isaac. If I have seen further than others, it is because I was perched upon the shoulders of giants. Who were some of these giants? Kepler, Galileo, Copernicus, Tycho. Maybe you could include Ptolemy in this list. Does science work this way today?